Okay, so now that we understand how important cones are for our color vision, let's get into some theories about color vision because there's even more to understand, as you might expect. So I'm going to try to be pretty quick here. Um, but we do need to understand there's different ways for us to understand color and how color even exists in our environment to some extent. That's not even true. Color doesn't exist in our environment. Technically, it exists in our brain, and that's a weird thing for us to understand. Um, okay, I was debating on whether to do this with you, and it's always a fun debate to have in class for a couple minutes. But arguably, think about it like this: it's kind of a philosophical thing. Okay, color exists in our brain based on what our eyes pick up from the environment, right? So think of it like this. Everything in our environment has a certain chemical makeup, whether it's the clothes we wear, the books we look at, the objects we see in our rooms, whatever. That chemical makeup makes it so that that object, whatever we're looking at, um, I have an ink pen here. This pen is made of a certain compound that absorbs certain wavelengths of light and reflects other wavelengths. Okay? So, assuming that light acts on waves as wavelengths, which is debatable still today and arguable, but let's just go with it. You have to understand that in white light, just all the light around you at any given time, if you could grab a handful of light, you can't. But if you did, I need you to understand that that white light that we're imagining you possess has every color of the rainbow in it. That's super important for where we're about to go. Okay? White light has every color of the rainbow in it. So when white light from the sun, from lamps, whatever, when white light hits this pen absorbs every color of the rainbow except red. Because of the chemical makeup of this pen reflects red light in all directions. And that red light, the red wavelengths, go into our eyes and start this process when we look at the pen. Okay? If we look at anything else, a purple pencil, this purple pencil is just like the pen, absorbing every wavelength of light except for purple, which reflects off into our eyes, starting off that chain reaction. That's always happening. Here's the debate part. Okay, quick riddle for you, quick question. If we're imagining it's wintertime and there's a foot of snow outside on the lawn, okay, we know there was green grass there yesterday, maybe brownish grass if it's wintertime, right? But now there's a foot of snow. Foot of snow outside on the grass. What color is the grass under the snow right now? What color is the grass? Did you answer green or brown, just like it was yesterday? Because here's a fun philosophical debate that would be fun if we were together right now. Arguably, no, that grass is black right now because black is darkness in this context. Black is the absence of light. And under a foot of snow, there's no light hitting that grass. So, hear what I'm saying. That grass contains chemical compounds that when light hits the grass, that grass will absorb every color of the rainbow except for green or brown or whatever we're seeing when light hits the grass. But under a foot of snow, there's no light hitting that grass. So in that moment, that grass is black. It has no color. Color exists not in the environment, but in our brains, folks. Color is the result of light hitting an object, that light bouncing into our eyes, starting off a chain reaction that ends up in the occipital lobe for our interpretation of, oh, look, green grass. Heavy stuff, right? It's crazy. It's good. I know it's good. I wish we were together right now. But anyway, okay. So now back to color theories. We've established some basics about color. Let's understand there's subtractive color mixing and there's additive color mixing. Subtractive is what we're most used to. This is what we've learned about since kindergarten, that if you're dealing with paints or crayons or markers or dyes of some kind, when you mix them together, you're going to get new colors. The colors aren't perfect on this slide, but like we got our primary colors, red, blue, and yellow. Those are the primary colors when we're dealing with subtractive color mixing. Red, blue, and yellow. If we have blue and yellow paint and we mix them together, we're going to get green paint. And I know you're confused because you're like, but we added the paints. Why is it called subtractive? Think of it like this. Here's a quick explanation, quick description anyway. It's because when you take blue paint and yellow paint and mix them together, that new mixture of paint is going to absorb more light out of the environment. It's going to suck more light out of the environment and reflect less, okay? That green paint is going to subtract more wavelengths out of the air and reflect a different amount. It's going to us is going to be green. Same thing, and I know it's not perfect on this slide, but if we mix red and yellow, the new mixture is going to suck more light, absorb light out of the environment, and what's reflected back is less than red and yellow individually, and we'll experience orange, okay? That's subtractive color mixing. And that exists, that's a thing, but that's not the only way that colors mix. We've also got additive color mixing, and this is when we mix colors of light. If you imagine being at a stage for a theater production, they have spotlights at the stage. Well, all they really need to show different colors of lights on the stage is 3 colors of light. They need red light, blue light, and green light. Imagine these are 3 separate spotlights. And notice the primary colors are different when we're talking about light colors, colors of light. Different than if we're talking about paint colors and the primary colors there. With additive color mixing, the primary colors are red, blue, and green. And if you take those 3 spotlights, the red, the blue, the green spotlights, if you shine them all 3 on a central point on the stage, you will get white light. Because white light is all the colors of the rainbow. These are the 3 primary colors of the rainbow. If you mix all 3 of those colors together at a central point, you will have white light, okay? This is how we say black is the absence of light when we're dealing with additive color mixing. If you want that stage to show blackness, you'd have to cut these lights out and have darkness to show black, okay? But if you're dealing with subtractive color mixing, if you want to make the color black, you mix all the paint colors together, because mixing all the paint would absorb more and more wavelengths of light out of the environment. Very little light is reflected back to our eyes, and we interpret that as black. By the way, that's why if it's a really hot summer day, maybe you don't want to wear a black t-shirt with black jeans, because the black fabric will absorb a lot of the light around you, a lot of the sun's energy, and it'll make you very hot. If you wear a white t-shirt, it will reflect a lot of the light, a lot of the energy, and maybe help you stay cooler on a hot day. But again, that's dealing with subtractive color mixing, dealing with dyes that make shirts and pants and things, versus additive color mixing. Make sure that makes sense, or else this next part is going to be very confusing. There are a few different theories about color vision that we need to understand, folks. The first one that came about in history, I believe, is called trichromatic theory. Trichromatic theory. If you break down that word, it literally means tri, 3, chroma, color. This is 3-color theory, also known as Helmholtz's theory. Some guy named Helmholtz came up with this idea, no disrespect, but anyway, I don't know that we need to memorize the name all that much, but maybe for multiple choice questions, which in 2020, we're not having on this year's exam. Anyway, trichromatic theory is based on the idea that we humans have 3 different types of cones inside our retinas. Remember, cones pick up color, right? So trichromatic theory says we must have three different cones, three types of cones throughout our retinas. And they're probably, look at my question here, those three different types of cones are likely to be based on the primary colors of light. So Helmholtz believed we have some cones in our retinas that pick up only red light. And right next door to them might be cones that pick up only blue light as it comes into the eye. And right next to those might be cones that only pick up green wavelengths of light as they come into the eye. So when we look at that red pen, on that point of our retinas where we're looking at the red pen, we've got cells picking up that image and firing red, red, red back to the occipital lobe to process that this is a red pen, okay? You're looking right now at my blue shirt and my red pen, just different areas of your retina. You've got blue cones firing to the retina, to the occipital lobe, and you've got next door to those in a slightly different part of your retina, the image of this pen, and the red cones are firing to the occipital lobe, telling them, oh, red pen, blue shirt, okay? You might be wondering, then how can we ever see yellow? Duh, like we don't have yellow cones? Well, according to Helmholtz, look at this diagram down here. When we see something yellow, maybe it's that the red cone and a green cone right next to it are firing simultaneously. And when the occipital lobe picks up those signals, oh, red, green at the same time, that's yellow. The interpretation happens that way. That's trichromatic theory, that we have three different types of cones in our retinas based on these primary colors. Now, I got to tell you, this isn't how it works. This is not true. This is a flawed theory, at least in the retina. It turns out this does not happen, and I'll show you why we know that in a second. But before I switch off this slide, I want to clarify. This is not what's happening in our retina, most likely, but trichromatic theory might be partially correct in our visual cortex, in our occipital lobe. We might have certain neurons that pick up red signals, other neurons that pick up green signals, and other neurons that pick up blue. And when one red neuron fires and another green one fires simultaneously, maybe that gives us yellow. There's some evidence that trichromatic theory might be kind of true in the brain, but not in the retina. And here's why. Stare at the white cross here, folks, in the middle of this screen, and just follow my instructions. Don't let your eyes wander too much. Just stare right at the center of that white plus in the center of your screen. And you can listen to me talk for a second. There's something that's going to happen in this next slide that is maybe going to be pretty weird to you if you've never experienced it before, but it's an experience that shows us that trichromatic theory cannot be totally correct. It cannot explain why this next phenomenon happens. I hope it happens for you. You can rewind and keep practicing again and again if you need, but keep staring at that plus, keep staring at that same area, even as I switch screens. Keep staring. Keep staring at the center. Now it's a dot. Keep staring. Maybe blink a little. And if nothing's happening, rewind a little bit, try it again. And when you get to this white screen, you can let your eyes wander a little bit. Look over at the white areas that are totally white. Yep, that's happening to me. Actually, if I look away from the black dot, I'm seeing a red, white, and blue American flag, even though I had been staring at a green, black, and yellow American flag. This is called an after image effect, where when you stare at certain colors and then look at a totally white environment, you will see an after image of completely different colors. Again, feel free to rewind, try this again and again, try to make it work. It usually works for most people. Just experiment a little bit, if you will. There is no red, white, and blue flag on this white screen. It does not exist. This is a totally white slide. But you're experiencing an after image, a color after image that's pretty crazy, especially since it's different colors than the image you were looking at. The question is, why does this happen? Well, it's not because of trichromatic theory. This theory can't explain the color after image, but this theory can. It's called opponent process theory. It's pretty important. It was developed by a guy named Edward Herring. Opponent process theory is based on the idea, as you see here, that we do not have three types of cones. It's not red, green, blue cones. No. Instead, Herring says we have three different pairs of cones. Pairs of cones. And the pairing works like this. Red cones are paired with green. When I do this with my hand, imagine that I've got like a red cone. When I say red cone, it's not colored red. Do you understand? It means this cone can only be stimulated by red colors. Red wavelengths of light are the only wavelengths that will stimulate this cone. And the green cone will only be stimulated by green wavelengths of light. And I'm doing it on my hand to symbolize the idea that these two cones are joined together at a base. Okay? These are pairs. I would almost call them partners, except no, they're not. They're not partners. They're opponents. This is called opponent process theory. This part's super important. They do like to ask about this a good bit on the AP exam. You ready? They're opponents. What that means is when the red cone is firing, bzonk, bzonk, I see a red pen, bzonk. When the red cone is firing, the green cone must be doing the opposite, which is resting. That means these two cones in this pairing can never fire at the same time. Remember how Helmholtz believed, oh, when a red cone and a green cone fire simultaneously, maybe that tells the brain, I'm seeing yellow. Opponent process theory says that can never happen. These two cones can never fire at the same time. When one of them is firing, the other one is resting, chilling. And when that one, the green cone, is firing, I'm looking at green grass outside right now. Bzonk, bzonk, the green cone is firing. Its red opponent has to rest. It has to chill. It cannot fire at the same time that the green cone is firing. That means you will never see anything that is reddish green in color. You can't. You can't see red and green at the exact same time in the exact same point in the retina. You might be saying to yourself, no, like I'm looking at a window over top my laptop right now, and I'm holding this red pen over my laptop. I can see the red pen and the green grass in the background. So I'm seeing red and green at the same time, right? Yeah, but not in this one pairing. As this image of the pen hits my retina, remember, there's tons of pairings all throughout my fovea, especially. That's where my cones are, in my fovea, remember? Okay, there's tons of these pairings. And in one of the pairings, I've got the red cone firing, telling me that I'm seeing the red pen. And the green cone down here is resting because the red cone is firing. And in a slightly different area of my retina, like right next door, I've got a red cone and a green cone over here too. And here, my green cone is firing because it's picking up the grass in the background. And as the green cone is firing for the grass, the red cone is chilling. The red cone can't fire because the red one is firing for the grass. But over here, the red cone is firing for the pen and the green cone has to chill. Does that make sense, everybody? The red cone's firing for the pen here and the green cone is firing here for the grass. It's weird what I'm doing here. I hope it's not a gang sign or something and I'm accidentally throwing up. But anyway, weirdest gang ever if that's happening. But make sure that's making sense. Opponent process theory says that this is happening all throughout the fovea. Wherever there's cones, the other pairings, look at them. I've got yellow and blue pairings. Wherever the yellow cone is firing, bzonk, whenever it's doing that, the blue one is currently chilling. And if the yellow one stops firing, then the blue one could fire. Okay? They can't fire at the same time within that pairing. And this theory says that we have cones for extreme black and white, okay? Where there's extreme black and white, not shades of gray, that would be our rods picking that information up. Wherever there's extreme black and white, we've got pairs of cones. If the black cone is firing, the white one is chilling. If the white one is firing, the black one is resting. That's opponent process theory. Now, why is that happening? Why is the after image happening? Try it again. As you're staring at this flag, look, wherever there's green stripes, you're stimulating the green cones in your retinas. And as long as the green ones are firing right now, which ones are resting? Which cones are resting in those stripes? Because remember, this image is on your retina. And wherever the green cones are firing, their red opponents, their red partners, they're resting. The reds are resting right now. Over here in the yellow field, you're stimulating. Keep staring. Keep working those cones, right? That sounds weird, but the yellow field, you're stimulating your yellow cones. So right there in your retina, your blue cones are currently resting. Wherever there's black, the stars, the stripes, the black cones are firing in your retina, and the white ones are currently resting. Now, whenever I change this slide, I'm not going to do it yet. Make sure you keep staring and you listen to me, okay? When I change this slide, it's going to be an all white slide. What colors of the rainbow are going to bounce off your screen from an all white slide? What colors are in white? All colors. All colors are in white light. So when I change this screen, you're going to experience an after image because white light and all the colors of the rainbow are going to course into your eyes, but your green cones are going to have to rest because we're going to have a changing stimulus. You're no longer going to be looking at green, black, and yellow here. You're going to be looking at, ready? Blank screen. That's almost all white. So all the colors of the rainbow are coming into your eyes, but your green, black, and yellow cones on those certain parts of your retinas, they have to rest because of the changing stimulus. And that leaves which cones to pick up this incoming light? Which cones had been resting but can now fire with the changing stimulus? Well, since the green cones have to stop firing with the changing stimulus, that leaves the red cones to fire in their place. And because the yellow cones have to stop firing because the slide switched, that leaves the blue cones, the blue opponents, to pick up this incoming light coming into your eyes. Okay? The opposite cones have to pick up this new information because their opponents have to now rest. And we see the after image of the red, white, and blue flag. Red, white, and blue being the opposites of green, yellow, and black. Not, and you know the orders, we went over that. But anyway, this color after image is evidence that opponent process theory is the accurate explanation of how we see. So we can do one more time. We can do one more example of this. Stare at these 4 dots right down the center here. You can stare right there. This is all monochromatic this time, extreme blacks and whites. Let this image burn into your retina a bit. Wherever there's black here, you're stimulating your black receptors, your black cones, so to speak. And again, wherever there's black cones firing right now in that same exact part of your retina, the white opponents are resting. And wherever you have white cones firing right now, right in those specific parts of your retina, you've got those white cones firing and their black partners are resting. The black opponents are resting in those pairs. White firing, black resting. Black firing, white resting. Their opponents. And we let that happen. We let that stimulate those cones nice and good, and then keep staring near the center. Or if it worked before to have your eyes wander, go ahead and do it again. And you should notice a face starting to appear. Somebody with long hair and a beard. Oh, it's really sinking into me. It looks really detailed, actually. And let's say it all together who that is on a count of three. 1, 2, 3. That's my Uncle Larry. That's a picture of my Uncle Larry. He's kind of a hippie, got long hair and a beard. That's Larry. I don't know if you know my Uncle Larry, but that you've seen his face now. That's him. That surprise you that that's Larry? Oh, did some of you think that was like Jesus? That's interesting, isn't it? Because this isn't any kind of spiritual or magical or religious phenomenon. It's just a matter of a color after image for all the reasons we've discussed. If you want an explanation on why this is happening, rewind, listen to it again so I don't have to repeat the whole thing. Okay? But here's the interesting part to me. We've given a bottom up explanation for how this after image happens because of opponent process theory. But just a little indicator, a nice little reminder, we also have some top-down processing happening. When this after image happens, you start interpreting, you use your schema to interpret what that after image is. It's not enough for us to just say, oh, that's weird, it's a face. No, you used your schema to tell you who that after image was of, like who that historical figure was or whatever. It could be my Uncle Larry. It could be Jesus. It could be, the guitar player from the Grateful Dead from the 1960s. Like it could be nobody. Like, how do we even know? For those of you that think it's Jesus, interesting philosophical conversation, borderlines on controversy. How do we know that that's what Jesus looked like anyway? What, from paintings that Renaissance painters did from Italy in the 1500s, making Jesus look like he had super light skin and straight hair, like he's a, resident of California or something? Like, I'm not sure Jesus, the historical figure. This is no disrespect to anyone or any religion. It's not even a religious conversation. This is talking about a historical figure, if nothing else. Regardless of what you believe, like everyone's entitled to their beliefs, but let's talk about schema. We have our schemas based on our experiences, right? We have our ideas of what anything or anyone is supposed to look like. Let's consider the historical figure of Jesus as a religious figure or not, just as a historical figure. I don't know that factually that he had very light skin and straight hair. He was a Middle Eastern man. Jesus was a Jew historically. He is seen religiously by Christians as the Messiah. And as we discussed the other day, Jews believe he's not the Messiah. Jews are still waiting on their Messiah, but Jesus himself was Jewish and a Middle Eastern man. There's a good chance he did not have very light skin and very straight blonde hair or anything that Renaissance painters may have depicted him as. So anyway, what's that have to do with anything? When you saw that after image pop up, it's interesting to think about the top-down processing that you used without even thinking about it consciously, how your schema came into play to tell you that, oh, that's crazy. This image is coming out of nowhere and I can't explain it. Like, we can explain it because we've learned about this in previous minutes of this presentation. But for other people who can't explain opponent process theory, they have this after image happen and they can't explain why it's happening. So it's unexplainable and it's kind of miraculous. So some people think it's a religious experience. And then it's an image of a man with a beard and long hair, and it fits their schema for Jesus. So this all comes together. And for some people, I've seen some people experience this as a spiritual, religious, amazing moment. And I'm not trying to take anything away from a person that would experience it like that. But we have these reasons to believe that it's just a matter of the bottom-up processing explained by opponent process theory and the top-down perception explained by schema and the fact that our brain always wants to make sense of stuff anyway. Pretty interesting stuff. So what do we got here? Let's not forget, as we learned in previous units, the visual field of our eyes is split in half, right? Just a reminder of that happening when we learned about split brain stuff. Let's not forget about how the optic chasm here is the part of the optic nerve where those images flip-flop to the opposite sides of our occipital lobe. Visual information does arrive at our occipital lobe at opposite hemispheres, right? Anything that's coming into the right visual field of my eye goes into the left occipital lobe for processing. The occipital lobe is where the primary visual cortex is located. And that's it for vision, folks. We'll pick up with hearing in the next chunk of video. Thank you.